Good morning, everyone. The topic of my talk is strategies to accelerate the energy transition using next-generation electrolyzer technologies for the green hydrogen production. My talk is outlined as such. Next slide, please. So first, I'll introduce my organization, TNO, who we are, TNO's hydrogen program, the key research challenges which we are covering up in our hydrogen program, the low iridium technology which TNO has developed, which is a promising solution for PEM technologies, the business cases, the current one, and the future prospects for the green hydrogen production. And finally, I'll sum up with the accelerating innovation. How do you actually accelerate innovations in large programs? TNO is a Netherlands organization for applied research. We connect people and knowledge to create innovation which accelerates the strengthening of the society and also boosts the competitiveness of the industry as a whole. So we have more than 3,800 staff. Majority of them are engineers, scientists who really work in the laboratory. And we also have more than 1,000 partnerships across industry and academia globally. And we have 42 professors working at TNO who are linked with different universities, and we have 800 plus patents as well as an organization. So if you look at the future market development forecast for green hydrogen, many speakers already talked about it. There are multiple aspects to be considered. The first one is a growth factor, which you see. By 2030, we are looking at a growth factor of 125. And this has an implication for the green hydrogen production capacities. And the forecast which give for the 2050, the growth factor really accelerates to 25,000. That's huge. And I will talk about the implications of this at later part of my presentation. Now we at TNO look at the integrated systems perspective on hydrogen. There is a demand side which has to be managed because of the grid stability and the flexibility, and there is a supply side which has to be managed. And hydrogen beyond fuel has significant consequences in the derivatives of hydrogen. And we are also looking into those aspects. How do we actually look into concepts such as power to X, using CO2 as an option as well. Our vision on hydrogen is to actually improve the integration of the renewable energy into the system and decarbonize hard-to-abate sectors such as steel, aviation, and other industries. So our vision in 2025 is to decrease the production cost of hydrogen electrolyzers by at least 30%. That's what we are aiming for in our research and innovation program. And reduce the use of scarce materials, the platinum group metals, which are used as catalysts for the PEM electrolyzer technologies. And also boost the success of the electrolyzer industry, especially related to the hydrogen production value chain. Not only in terms of the production and distribution, but also how do you actually boost the production of the technologies. So the supply chain of the technology is also a critical element here. So TNO's green hydrogen activities aim to actually deliver technical, social, and the innovation angle to accelerate the development of the hydrogen programs. And we look at the problem at a systems level. How do you actually integrate technology development and the technology value chain development and the overall system as a whole? Most importantly, the infrastructure, which is a critical attribute in terms of the development in the society. Now, there are critical trade-offs which are actually important. The three attributes here are the efficiency, durability, and the capex. And this arises from the cell design, which could be from the catalyst loading or the membrane thickness that actually leads to these trade-offs, or the operating parameter tuning, such as high temperature and high pressure, the high current loadings. And this has naturally its consequences on the three trade-offs, which is on the durability aspects, the efficiency, and the capex on the electrolyzers. So we look at the hydrogen from a systems perspective, as I said. So the concept of hydrogen electrolyzer generations is something which we have looked into. So, and its role, what TNO can play in. So for the first generation electrolyzers, where the technology is already in place, these are commercial technology, and OEMs are already active. We as TNO see our role as integration support. For the second generation technologies, the development of the improved components, such as membranes, electrodes, or coatings, we look at our role as accelerating the innovation on how do we actually accelerate the innovation and bring it faster in the market. And the third one is in terms of radically new concepts or architectures on the cell design and also looking into the breakthrough performance. We look ourselves in terms of the creating new innovations or the new inventions to cater to the third generation. And there is a whole program actually which is lined up to tackle into these three generations of the electrolyzer technologies. As a snapshot, there are multiple players who are already active in different technologies for electrolyzers, and the list is growing. And I'd just like to give you a flavor. We are quite actively active in the PEM technologies and the solid oxide, again at different levels of technology development because currently they are at different TRL levels, and AEM as well. And beyond that, there are different research institutes and organizations who are looking into new electrolyzer concepts and the integrated approach as well. Now, I talked about the scale and durability. So there are certain aspects which we aim for. So current state-of-the-art technology could deliver only at a certain level, and it's not enough. And there are hard targets to be placed, which have been placed to develop for 2030, and there are natural consequences for it. On, for example, how do we actually reduce the use of critical raw materials from a certain usages to a factor or two lower than what we use in the electrolyzers as of now. And naturally, it has its own implications to the system efficiency and how do you maintain the system efficiency even though when you use less critical raw materials in usage. Now, to give you a flavor here, the electrolyzers capacity as they will ramp up in the future and in 2030 and beyond, the current usage levels, if you project it on a per megawatt capacity for the electrolyzers, you use 800 kilograms of nickel as of now from the alkaline-based electrolyzers. But from the PEM electrolyzers, platinum group metals are really critical here. So there are a few kilograms or a few grams of platinum and iridium, which are used on a per megawatt capacity for the PEM electrolyzers, and it has its own consequences. If you look at the critical raw material supply chain, 3 countries really possess it in large quantities, the iridium and platinum metals. And these are South Africa, Russia, and Zimbabwe. So there are supply chain constraints which come up into picture because there is a concentration of the raw materials in only few geographical locations globally. And there is also a constraint in terms of how much we can actually use from the current capacities of these materials which are available globally. So we did an analysis on different strategies to use the current iridium and platinum and other materials requirement. In the base case scenario, for 2030, for the projected global capacities for PEM electrolyzers, there is not sufficient capacity for iridium to be produced, which is 122% as a whole. For Europe itself, if we have to achieve the Europe's 2030 targets, 47% of the iridium capacity of global have to be channelized through PEM electrolyzer production. Naturally, there will be consequences in terms of delayed installation or delayed development of the technology. So the reduction is one strategy which we believe which provides the most potential. And how do we actually achieve through it? So there are technologies which TNO has developed in terms of PEM, next generation PEM technologies, where we reduce the iridium consumption in the PEM technology by 200 times. And similar technologies have to be developed on how do you actually maintain the system durability and efficiency in the long run, reducing the requirement of your catalyst so that your back-end supply chains are well protected. Otherwise, there will be a huge challenge. Now, switching gears in terms of the business case for the electrolyzers, especially for PEM here. So there were different scenarios run, and for the electricity price, if you look for the electrolyzers, hydrogen production cost, the main component here is the electricity cost really drives the overall production cost for hydrogen. CapEx is a contributor here, but not the differentiator. And naturally, this will also reduce over a period of time. But if you look at the flexibility as a context, when you try to use electrolyzers in flexible mode, CapEx becomes the dominant factor as expected. And now the business case becomes even weaker from the standard operating conditions when you run the electrolyzers for 800 hours. Now the challenge is how do you reduce the stack cost or the balance of payment, balance of the plant cost to actually make CapEx as a lower contributor compared to the OpEx cost for the flexible operations. And flexibility is all thought as a solution as a whole, but personally, as an expert, I believe it will still take long time for use of hydrogen as in terms of flexible scenario, primarily because of the hindrance in terms of the CapEx installations here. There is another concept in terms of how the cost of production for a technology evolves over a period of time. If you look at the forecasted CapEx cost for 2000, as the cumulative capacity builds up over the years for the PEM electrolyzers, there have been certain forecasts placed by different organizations such as IRENA, IEA, McKinsey, and there is a 12 to 20% learning rate with each additional capacity additions to reduce the CapEx cost by a certain level. Now, the challenge is how do you actually meet these learning rates? That's a basic challenge which a typical like research and development team actually struggles with. The other one is if you have to meet that 25,000 times capacity addition target, these learning rates will not be sufficient. How do you then accelerate these learning curves is a question which is still on the table for discussion and also in terms of strategy development. And what will be that learning rate is also to be determined. And this is what my team is working on what is the learning rate we need to actually lower the the overall cost of production of hydrogen in the long run as the cumulative capacities add up over the years. And yeah, one comment on the previous slide is PEM and solid oxide technologies will actually benefit because of the complement they get from the fuel cell developments in the long run. So their capacity, their learning rate will be faster than the mature technologies. Now we look at the entire system holistically, not only the production chain of hydrogen. There are technology providers who have to be also integrated to actually touch upon the various hotspots which have to be channelized or controlled. And then there are high-tech equipment and material suppliers who are the suppliers for the technology providers. So there are 3 layers of the value chains, not only the production value chain, that have to capture it well. And we try to bring all these partners together and try to accelerate technology development and address the research challenges as they come up during the technology development pipeline. Now, what we contribute towards acceleration of the technology development is we have certain research facilities at lab scale, few kilowatt scales, and we also have certain demonstration scale facilities in terms of 100 kilowatts to 1 megawatt. And then there are demonstration scale facilities which are multi-megawatt, which are in progress through different B2B or consortium funding programs or through the European Commission projects as well.
1 more minute.
So, thanks, Chair. So we have 5 pillars for our added value in the electrolyzer value chain, and we believe that we are acting as an orchestrating innovation to connect the ecosystem for innovation implementations. And these 5 pillars are system integration, accelerating the learning curves, as I mentioned earlier, next generation PEM technologies, the second and the third generation is critical, how do we contribute there, and the second generation solid oxide technologies, and also looking into the breakthrough innovations such as AEMs. So summing up, we look into the rapid prototyping as an option, acceleration of the lifetime validation and benchmarking at lab scale and also at pilot scale, and also supporting the industry in terms of building industrial scale R&D stacks so that they can test it out, the equipment in the field. And we have one of the largest open electrolyzer test center located in the Netherlands, which is looking into development of the megawatt test facility. And we also support in terms of modeling the thermal behavior of the stack and also advanced process control. So we cover the technology development and also trying to build the reliability of the system as a whole in terms of through this test performance equipment we have. Now to just sum up, I would like to invite others, if you are interested in learning more about a hydrogen program, please connect with me or my colleague Leonard, and we will be happy to actually answer your queries and look forward to actually future opportunities for collaboration. Thank you very much.